Hello, and welcome to the first lesson in pre-calculus. We just finished up our in calculus. Sorry, we just finished up our pre-calc review. We're going to need all those skills as we move forward. And what you're going to notice is that calculus looks at, and especially the first half, it looks at slope, and it just looks at slope in a way that you've never looked at it before. So our first lesson might seem a little redundant, like we're back in algebra 1. That's because slope is the basis of calculus. And when we're thinking about slope, we're thinking about the rate of change between 2 points. So if I had a point x, I don't like this color. Let me see if I can get a new color here. There we go. Okay. If I had 2 points such as x1 and y1 and x2 and y2, you all learned the slope formula back in 8th grade, 7th grade, that it was just the y2 minus y1 over x2 minus x1, right? But instead of looking at it as y2 minus y1, we're now in calculus, so we want to start using math symbols. So instead of saying y2 minus y1, we're going to say change in y. All right. Instead of writing change in, we're going to use this symbol here. It's called a delta. Okay, it looks like a triangle. So we're going to say it's delta y over delta x. Right? Change in y over change in x. Okay. Another way you might see it, right? If you think about this point, instead of writing it as x1 y1, you can write it as x1 comma f of x1, because f of x1 really represents y. And then we have x2, and this is f of x2. Okay? Because, again, the function value is the y value. So you can think of slope as f of x2 minus f of x1, right? The difference in the y values over the difference in the x values. So all three of these formulas mean the same thing, right? Change in y over change in x. Okay, that's the slope, which you've seen before. Velocity. Think about velocity. The speed that something is going, how fast a car is going, and you find velocity by looking at the change in position over the change in time. All right, or you can write it as the change in position over the change in time. And velocity is really a slope. It's a rate of change, because it's how fast something how fast a position is changing with respect to time. Okay, which is just delta y over delta x, or delta position over delta time. And in this unit, we're really looking about velocity, because velocity is a slope, and velocity has two different meanings. We have average velocity, and we have instantaneous velocity. And today we're going to analyze the difference between an average velocity and an instantaneous velocity. Okay. So we have average and we have instantaneous. The average velocity, like I said, is just change in position over change in time. So if I was in a car and I was traveling to, I don't know, let's go to Boston. I'm in a car and I'm traveling to Boston, and it's 200 kilometers to Boston, and it takes me 4 hours. The average velocity, according to my little formula, says change in position over change in time. So that would be 200 kilometers, because I went 200 kilometers, and the total time it took a change in time was 4 hours. So therefore, my average velocity was 50 kilometers per hour. That's a rate of change. That's how many kilometers I was going per hour. Okay. However, was I really going 50 kilometers per hour the whole way there? Probably not. Somewhere along the way, I was going to have to stop and use the bathroom. Okay, so at that point, I was going 0 miles per hour, or kilometers per hour. And there were times when I was on the turnpike or the parkway, and I was going faster than 50 kilometers per hour. So while 50 kilometers per hour is the average speed that I was going, or average velocity, it's not the instantaneous velocity. I wasn't traveling that speed the entire time. So let's say that you called me on my cell phone on somewhere on my trip, and I was about 3 hours into my trip, and you were like, "Hey, Mr. Walsh, how fast are you going right at this moment?" That would be the instantaneous velocity. An instantaneous velocity is velocity at a particular moment in time. However, it's very difficult to find the instantaneous velocity. Think about it. Velocity is change in position over change in time. Instantaneous velocity is a velocity at a very particular moment in time. So if I had change in position over change in time, but if I'm talking about a single moment in time, that means that the change in time is zero. My denominator is zero because there is no change in time. It's at a split second, a particular moment. You can't divide by zero. So there has to be other ways to estimate or find the instantaneous velocity, because this little formula is not going to work for us because our change in time will be zero if we're looking at instantaneous velocity. It works for average velocity, but it doesn't quite work for instantaneous. So we're going to figure out how can we go ahead and find instantaneous velocity. Well, this is the formula that I just showed you that talks about average velocity. In calculus and physics, for those who have taken physics before, usually a position function is s of t. Right? So instead of using f of x, where x is your input and f is your function, right? Input. And instead of using that, we use s of t. Because usually when we talk about velocity and position, we're talking about t is time, and then s is the position. Okay, that's why it might look a little funky. So instead of it being delta y over delta x, they call it delta s over delta t. Okay, and that's the average velocity over some time interval. So instead of using x's and y's, they use t's and s's. And you'll see it in physics, you'll see it in calculus. So just kind of get used to that notation. All right, let's look at an example. A stone released from the state of rest falls to Earth. Estimate the instantaneous velocity at 0.8 seconds. Okay, so that means that we're looking at the velocity at exactly 0.8 seconds. How fast am I going 0.8 seconds after I release the stone? Okay, so the object is released, called time t is 0. So as soon as I release it, that's where 0 starts, and then it goes, seconds go from there. The distance traveled after t seconds is given by this function. So this is my position function. Now we said that we can't find instantaneous velocity because that means that my denominator would be 0. So instead of finding instantaneous velocity, let's have another idea. Let's find the average velocity, which we can find, between two very close points, right? So instead of looking at it at just 0.8 seconds, let's find the velocity between 0.8 seconds and 0.81 seconds. So it's 1/100th of a second difference. We can do that because now my denominator is no longer 0. Okay, my change in time is actually a number as opposed to 0. So if we find the average velocity of two very close moments in time, we can at least estimate how fast it's going at 0.8 seconds. So again, my average velocity is going to be s of t1 minus s of t0 over t1 minus t0. That was the formula that was given to us in the last slide. Now this right here is t0 and t1. So we're looking at the time interval of 0.8 seconds to 0.81 seconds. Looking at the average velocity to try to estimate instantaneous velocity. So we're going to plug these values into this little formula. So we're going to find There's a color here. We're going to find s of 0.81 minus s of 0.8 all over 0.81 minus 0.8. So we're going to use our calculators. We're going to input 0.81 into this function right here, right? It's the position of my stone at 0.81 seconds minus the position of the stone at 0.8 seconds. So when I input these two values into this function right here, I end up with 3.21489 minus 3.136 divided by the difference between these two values is 0.01. When I do that, I end up with 7.889. Now again, this is a rate, so because it is change in position over time, we're talking about, let's see, meters maybe? Yes. So we'll go meters per second. Okay, this is the average velocity that the stone is falling between this very close time interval, 0.8 and 0.81 seconds. Now, is that the instantaneous velocity at 0.8 seconds? No, but it's very close. Well, we're actually able to get even closer. So here, we looked at the difference of 1/100th of a second. Let's look even closer, okay? Instead of being 1/100th of a second, let's look at the difference between 0.8 and 0.805. So it's 5/1000ths of a second. So we're gonna do the same thing. We're gonna find the average velocity between these two this time interval, and we're going to see if we can use that to estimate the instantaneous velocity, because we can't find instantaneous velocity because the denominator cannot be 0. So again, I'm going to do s of 0.805 minus s of 0.8 divided by 0.805 minus 0.8. I'm going to take these values and input them into my function. And when I do that, you're going to get some long decimals. 3.1753225 minus 3.136 divided by 0.005. And this value right here is 7.8645 meters per second. A little bit different than the number we got here. All right, 7.889. This is 7.8645. Very close, but a little bit different. So the question is, which one's right? Which one is the instantaneous velocity? Well, the answer is neither. Both of them are still average velocities of very small time intervals. They're very close to the instantaneous velocity, but it's not quite. In fact, these two numbers can continue to get smaller. They get closer together. The difference between these two guys can get really, really close. So I'm not going to do it. Instead, I'll show you a chart, right? These are the two we already did. We found this value, and we found this value because we looked at the time interval between 0.8 and 0.81, and then 0.8 and 0.805. And if we kept doing this, if we did 0.8 and 0.8001, you would get this average velocity. And if you looked at the time interval of 0.8 to 0.80005, you would get this average velocity. And if you did the time interval between 0.8 and 0.80001, you would get this average velocity. And what you'll see is that as the time intervals get very close, the average velocity seems to be approaching some number. And that number looks like it's going to be 7.84 meters per second. And that is estimating the instantaneous velocity. This is my best guess at the instantaneous velocity. So we found the average velocity of a time interval that was really close together and used those values to help us estimate the instantaneous velocity. since instantaneous velocity can't be found because you cannot divide by 0. Okay? Now, what did we just do? Graphically, this black line here is my position function. Okay? So black line's position. This blue line represents what's called a secant line. Now, a secant line is a line that goes through 2 points. 1, 2. See that? Okay? Finding the slope between these 2 points is finding the slope of the secant line. Right? If I found the slope between this point and this point, which is just the slope of the blue line, that is the slope of the secant line. The average velocity is just the slope of a secant line. Okay? Now, if you look at my x values is time. Here's time 0 and here's time 1. I mean, it corresponds with this point here and with this point here. Now, this time interval looks very big, and that's why this slope, this secant line, doesn't actually, it goes through the 2 points. If I brought these 2 time intervals closer together, right? If I took this interval and moved it this way, right, and I went to here. Here would be my value, and this would be my secant line. See that? Okay? Or if I got even closer, right? If I took my time interval and I squish it together until these 2 points were almost on top of each other. And now my secant line looks like that. Right? And that's what we're doing. We're taking 2 points, 2 x values, 2 time intervals, and we're bringing them really close together because the average velocity is a secant line, but the instantaneous velocity is a tangent line. Okay? Now, a tangent line is a straight line that intersects the graph at 1 point, but does not go through the graph. Right? For example, you see this line here? This is a tangent line. And if I was to draw a function, there it is. This right here is a tangent line. It intersects right at this 1 point. And the slope of a tangent line is the instantaneous velocity. So our task in this image here, if I wanted to find the slope or the velocity at this point, I had to bring these 2 x values really close together so I can estimate what that what that tangent line slope would be. And that's what we were doing. We were finding essentially the slope of the tangent line at the x value of 0.8 seconds. Because the slope of the tangent line is the instantaneous rate of change, also known as the instantaneous velocity. So we have secant lines and tangent lines. Secant lines, average rate of change. Tangent lines are instantaneous rate of change. So our job is going to be to find the slope of tangent lines, and we're going to use secant lines to help us estimate the slope of tangent lines. Oops. There we go. Okay. Now, so again, the average velocity is the slope of a secant line, whereas the instantaneous velocity is the slope of the tangent line. As the time interval shrinks to 0, right, as that time interval gets closer and closer together, the slope of the secant line, which we said is the average velocity, approaches the slope of the tangent line. Right? So again, as that time interval gets really close together, so here is that image here. As this time interval gets closer together, these 2 points will get closer together, and this secant line will start looking more and more like a tangent line. So as the time interval shrinks to 0, the slope of the secant line approaches the slope of the tangent line. And that's because a secant line is the average velocity, and a tangent line is the instantaneous velocity. We're using secant lines to estimate tangent lines. We're using average velocity to estimate instantaneous velocity. Okay, let's look at one last example together. A ball is dropped from a state of rest at time t equals 0. The distance traveled after t seconds is this function here. Okay, this is our position function. Position. Okay. Compute the average velocity over these time intervals. After computing this, use it to estimate the ball's instantaneous velocity at 3 seconds. We're trying to figure out exactly how fast this ball is falling after 3 seconds. So we're going to use the average velocity to estimate that value. Again, average velocity is change in y over change in x, or change in position over change in time. So we're going to do s of 3.01 minus s of 3 divided by 3.01 minus 3. So I'm going to pull out my handy dandy calculator and plug in some values. Here I get 144.9616 minus 144 divided by 0.01. I end up with 96.16 is going to be feet per second. Again, this is the average velocity in the time interval of 3 to 3.01 seconds. So in that split second, right, in between the 3 seconds and the 3.01 seconds, the ball was falling at a rate of 96.16 feet per second. But we can get this time interval closer together. So we're going to try the next one, which should be s of 3.005 minus s of 3 over 3.01 minus 3.005 minus 3. Now I know this value already is 144. I know my denominator will be 0.005, and then I'll use my calculator to do 3.005, square it, and multiply by 16. Oops. And I get 144.4804. And then here I get 96.08 feet per second. Okay, so a little bit different. Our job is to see if this approaches any specific value. I'm just going to erase this so I have some room here. Okay. Again, we can get our intervals even closer. So we'll do s of 3.001 minus s of 3 over 3.01001 minus 3. I'm not going to write out all these values. I'm just going to use my calculator to find it. And I get 96.016 feet per second. And we're getting closer. So if you're asking me at this moment, my guess is that it's going to reach 96, but let's just try it one more time. Okay, so now this is 1 1/1000th difference. This is 5/10,000ths difference. So it's 3 to 3.0005 seconds. So very close time intervals, but not 0, which is the important part. We're not dividing by 0. The difference between these two times is not 0. So it's going to be S of 3.0005 minus S of 3 over 3.0005 minus 3. Again, I will use my calculator. I get 96.008 feet per second. Okay, so again, our job is to use it to best estimate the instantaneous velocity. I would use this number right here, or if you wanted to go all the way down to 96. So if you look at this and you make a conclusion, you said, you know what, all of these numbers are getting really, really close to 96 feet per second. I'm going to make the conclusion that says that this ball at 3 seconds is falling at 96 feet per second. And that is how we use the average velocity to estimate the instantaneous velocity of an object, whether it's a ball falling or a car moving. We're using average rate of change to estimate instantaneous rate of change.